Dear Professor Danninger, dear guests, it is my great honor and pleasure to open this ceremony and to welcome here the visit of a very, very high-level specialist and scientist which is cooperating with our institution. Stimați invitați, este o plăcere pentru mine să coordonez această festivitate în numele domnului rector, să spun bun venit domnului profesor. Este ceremonia de acordare a titlului doctor honoris causa domnului profesor Herbert Danninger la propunerea Facultății de Mecanică și a Departamentului IMTS de la Drobeta Turnul Severin. Vă rog să permiteți să adresez invitația domnului decan al Facultății de Mecanică să citească laudațiu.
Domnule profesor Herbert Danninger, doamnă prorector, domnilor prorector, stimați membri ai prezidiului, stimat auditoriu, în calitatea de decan al Facultății de Mecanică din Craiova, permiteți-mi să vă spun doar câteva cuvinte despre facultatea noastră, înainte de a da citire acestui laudațiu care este absolut deosebit. Facultatea de Mecanică din Craiova este una dintre cele mai importante, mai frumoase și mai mari facultăți ale Universității din Craiova, în care își desfășoară activitatea aproape 2000 de studenți, care sunt coordonați și conduși de un corp profesoral puternic cu multă experiență, care este format din aproape 90 de cadre didactice titulare, organizate pe 3 departamente, 2 departamente la Craiova și un departament în orașul Drobeta Turnul Severin. Facultatea de Mecanică este importantă pentru că gestionează în acest moment poate cele mai frumoase domenii ale ingineriei, și anume este vorba de domeniul ingineria materialelor și ingineria mediului, ingineria automobilelor și ingineria transporturilor, ingineria industrială și domeniul inginerie și management și respectiv ingineria navigației și ingineria civilă. Facultatea de Mecanică în acest moment oferă cadrelor didactice și studenților ei condiții excelente pentru dezvoltarea unui proces educațional de înaltă calitate și de asemenea și de cercetare. Direcțiile de cercetare ale Facultății de Mecanică sunt perfect axate pe domeniile pe care le gestionează Facultatea de Mecanică în acest moment. De aceea, ce se întâmplă astăzi nu este întâmplător, pentru că astăzi Facultatea de Mecanică trăiește un eveniment deosebit, este un eveniment important și eu, în calitatea de decan, am onoarea să prezint acest laudațiu pentru profesorul Herbert Danninger, care este într-adevăr unul deosebit și vă rog să-l ascultați. Laudațiu în onoarea domnului profesor universitar dr. inginer Herbert Danninger, decan al Facultății de Chimie Tehnică, Universitatea Tehnologică din Viena, Austria, cu ocazia decernării titlului doctor honoris causa al Universității din Craiova. Propunerea Consiliului Facultății de Mecanică a avut ca reper personalitatea profesorului, inginerului și cercetătorului Herbert Danninger, unul dintre cei mai recunoscuți și apreciați reprezentanți ai unor prestigioase organizații europene și internaționale din domeniul metalurgiei pulberilor, tehnologie de fabricație a materialelor avansate pentru aplicații industriale de vârf. Titlul pe care îl decernăm în cadrul ceremoniei reprezintă recunoașterea, aprecierea și considerația cadrelor didactice universitare, a cercetătorilor și specialiștilor din universitatea noastră, deoarece domnul profesor Herbert Danninger este o voce și reprezintă un nume al comunității științifice cu o amprentă marcantă în domeniul materialelor și a tehnologiei avansate în fabricare în ultimii 30 de ani, la nivel european și internațional. În anul 1979, odată cu absolvirea studiilor universitare în domeniul chimiei tehnice la Universitatea Tehnologică din Viena, domnul profesor Herbert Danninger devine inginer chimist, ceea ce a reprezentat debutul unei cariere științifice și de cercetare de excepție. Specializarea domnului profesor Herbert Danninger în domeniul aliajelor dure pe bază de Wolfram se materializează prin finalizarea studiilor doctorale în anul 1980, iar abilitarea pentru conducere de doctorat este susținută cu succes în anul 1990 în ramura metalurgia pulberilor, respectiv tehnologii avansate de sinterizare cu fază lichidă tranzitorie. Încă de la început, cariera științifică și de cercetare a domnului profesor s-a dezvoltat armonios vizând domeniul dezvoltării materialelor avansate, colaborat cu cele mai moderne și eficiente tehnologii de fabricare, care se asigură performanțele deosebite de aplicațiile industriale de vârf. Pe de o parte, studiile domnului profesor s-au concentrat pe aliajele bifazice de wolfram, respectiv oțeluri speciale a căror sinteză necesită tehnologii avansate de obținere. Procesele inovative de compactizare a pulberilor în vederea obținerii de materiale de înaltă densitate și esență mecanică au fost ingenios combinate cu metode de tratament termic special proiectate. Scopul principal al cercetărilor întreprinse a fost de monitorizare și coordonare a proceselor fizico-chimice desfășurate în timpul încălzirii materialelor, astfel încât să se obține un efect maxim al tratamentului termic în condiții de minim consum energetic. Pe de altă parte, domnul profesor a întreprins cercetări de anvergură în scopul determinării corelației dintre microstructura și proprietățile mecanice ale oțelurilor sinterizate, în special în vederea analizei comportamentului la oboseală acestora, respectiv al îmbunătățirii acestuia prin tratamente termice post-sinterizare. Viziunea pe termen mediu și lung a domnului profesor Herbert Denninger în domeniul aplicațiilor materialelor avansate cu structuri speciale, neconvenționale, a permis conectarea armonioasă și eficiența cercetării științifice întreprinse cu mediul european economic și de afaceri. Cultura antreprenorială a domnului profesor a condus la dezvoltarea de aplicații industriale de nișă pentru companii industriale de renume din Austria, din Suedia, din Liechtenstein, din Elveția, din Luxemburg sau din Germania. Rezultatele excepționale ale activității de antreprenoriat ale domniei sale, permanent, riguros organizate și prezentate, au fost larg apreciate de mediul de afaceri, de practicieni și teoreticieni, precum și de studenți, masteranți și doctoranți. Întreaga activitate de cercetare, dezvoltare, inovare a domnului profesor este confirmată odată în plus de publicațiile de o înaltă valoare științifică și tehnică la nivel european și mondial. Manuale de specialitate, între care amintim oțeluri fabricate prin metalurgia pulberilor, Powder Metallurgy of Steel, editura Springer Verlag, anul 1992, prelucrabilitatea oțelor fabricate prin metalurgia pulberilor, Machinability of Powder Metallurgical Steels, editura Cambridge International Science, anul 2005. Fenomenul de oboseală în materiale poroase, Fatigue of Powder Metallurgy Materials, editura Elsevier 2001, materiale ușoare fabricate prin metalurgia pulberilor, Powder Metallurgy Lightweight Materials, editura Wiley 2009, reprezintă corolarul rezultatelor de un alt nivel științific și de o reală utilitate practică, diseminate inclusiv în peste 400 de lucrări științifice de specialitate. Încununarea acestor realizări marcante s-a materializat prin numirea domniei sale în funcția de editor șef al revistei Metalurgia Pulberilor, Powder Metallurgy, editura Taylor and Francis, pe care din anul 2004 o desfășoară la cel mai înalt nivel profesional, împreună cu domnul profesor José Manuel Torralba, Universitatea Carlos al III-lea din Madrid, de asemenea doctor honoris causa al Universității din Craiova. Profesorul Herbert Denninger a dezvoltat de-a lungul anilor colaborări cu universități și institute de cercetare cum sunt Universitatea Johannes Kepler din Austria, Universitatea Tehnică din Dresda, Germania, Academia Slovacă de Științe, Universitatea Carlos al III-lea din Madrid, Spania și Universitatea din Trento, Italia, reprezentând o punte solidă între cercetare științifică și aplicativă dintre Europa de Vest și Europa de Est. În peste cei 35 de ani de carieră, profesorul Herbert Denninger a obținut premii și nominalizări de referință în domenii, dintre care cele mai recente sunt doctor honoris causa al Universității Tehnice din Cluj-Napoca în 2010, respectiv Universitatea Carlos al III-lea din Madrid 2016, precum și premiul Asociației Americane de Metalurgie a Pulberilor, APMI International Princeton, USA, în anul 2010. Colaborarea dintre Universitatea din Craiova și Universitatea Tehnologică din Viena, inițiată de domnul profesor Denninger, a fost susținută de-a lungul a peste 15 ani de domnul profesor Mario Rosso, Universitatea Politehnica din Torino, Italia, doctor honoris causa al Universității din Craiova în anul 2004, respectiv domnul profesor José Manuel Torralba, Universitatea Carlos al III-lea din Madrid, Spania, la rândul său, de asemenea, doctor honoris causa al Universității din Craiova în anul 2007. În această perioadă, 2000-2010, cooperarea dintre Universitatea Tehnologică din Viena și Universitatea din Craiova s-a manifestat prin derularea de activități educaționale și de cercetare în domeniul metalurgiei pulberilor până la nivelul Asociației Europene de Metalurgia Pulberilor. Astăzi, Senatul Universității din Craiova își aduce contribuție la consolidarea acestei recunoașteri europene și internaționale. Prin înscrierea domnului profesor universitar dr. inginer Herbert Denninger în rândul membrilor comunității academice a Universității din Craiova și decernarea prestigiosului titlu Dr. Honoris Causa, ne exprimăm considerația, prețuirea și recunoștința față de o personalitate marcantă a domeniului tehnologiei și materialelor avansate, față de un profesor, cercetător și manager de cel mai înalt nivel. Prin acordarea acestui titlu, recunoaștem meritele și contribuțiile domniei sale la dezvoltarea de soluții inovative în domeniul ingineriei chimice pentru aplicații industriale de vârf și în susținerea afirmării pe plan național și european a învățământului tehnic, cercetării științifice aplicative și a profesiei de inginer chimist. Datat Craiova, 15 noiembrie 2016. Mulțumesc!
Avem acum o imagine și mai completă despre valoarea realizărilor științifice, despre personalitatea celui pe care astăzi îl celebrăm și pe care îl includem în categoria dragă nouă tuturor a doctorilor honoris causa a Universității din Craiova. Ca să nu lungim foarte mult această includerea domnului profesor, dați-mi voie să dau citire diplomei prin care domnului profesor îi se acordă titlul de doctor honoris causa al Universității din Craiova. Senatus Universitatis Craiovensis, Rectore Magnifico Cezar Ionuț Spânu, Professore Publico Ordinario, Sumo Omnium Plausud decrivit ut illustrissimum Dominus Herbert Denninger in corpus doctorum universitatis honoris causa recipetur, in cuius rei fidem hoc diploma conscribendum censuit Cezar Ionuț Spânu, rector magnificus. România, datum Craiove, die 16 mensis novembris, anno domini bis millesimo, decimo sexto. Viva Academia! Viva profesores! Viva Academia! Viva profesores! Viva membrum Domine! Viva membra Domine! Semper signum
Dear members of the University, of the Rectorate, of the Senate, dear colleagues and friends, I'm very proud to be awarded the Doctor Honoris Causa of your renowned university. Well, Doctor Honoris Causa in the academic world is a very, very high honor to be awarded. I would say it's virtually the highest honor a university can give. And I'm extremely proud to bear this coat and to carry the hat that shows me to be a member of your university, a Doctor Honoris Causa. Once more, many, many thanks. Well, I shall remember this day. Well, my first lecture shall first of all give you some idea about the place I come from, my university. You see it here on the screen. This is the main building of Technische Universität Wien, Vienna University of Technology. Here you see on the description, it's the old name Technische Hochschule we had until 1975. But also the motto, this on top, that means we are dedicated to improve life for the people according to our motto, Technik für Menschen, technology for humans. What is now this university, which, by the way, had its 200th birthday almost exactly 1 year ago, on 6th of November in 2015. Well, here a few dates and facts. I'm a technologist, therefore I can't do without dates and facts. We were established in 1815 as the Royal Imperial Polytechnical Institute, and as you will imagine, we had a big party last year. In 1872, we became a Technische Hochschule, Technical High School, and in 1975, we were promoted more or less to Technische Universität, to university, but the most, let's say, decisive change was in 2004, when we became a legally autonomous body, run to some extent like an industrial enterprise, no more as a subsidiary of the Ministry of Science. We are now funded to a large extent by federal money, by the ministry, but we also acquire quite a lot of money from third parties, mostly from grants, from projects. I'll show later on where this comes from. Here, a few data. We have at the moment 143 full professors, close to 4,000 scientists, and of course also technical administrative staff, 30,000 students, which is quite a lot to handle, as you will imagine. Among them is more than 1/4 female students, and this trend is increasing. And we also have a huge proportion of non-Austrian students. On both fields we are quite proud. Of course, we have also graduates, and we are awarding about 260 doctorate degrees per year. And let's say the doctors, they're our main product, and they end up mostly in leading positions in the industry, or also, of course, in the academia. From the time we became independent and autonomous, we had 8 faculties. You see on the screen, it's well, as more or less those faculties you would expect at the University of Technology. I'm from the Faculty of Technical Chemistry, and therefore this is written in bold. Here you see our current rectorate, which is not so much a honorary position, but it's really a management position, because the rectors are actually responsible for all aspects at the university, like the general manager of a company is. You see, we have our rector in the center, Sabine Seidler, a material scientist, by the way, and then we have the rectors. On one side to her is Anna Steiger, who is vice rector for human resources. Next to her, our Kurt Matthias, our vice rector for education. On the other side of the rector, a very important person is Josef Eberhard Steiner, vice rector for infrastructure. And on his side is Hannes Fröhlich, vice rector for research and innovation, and my predecessor as dean of the faculty. Well, here you see our research activities, the research matrix. We have in principle 5 focal areas. I'm working mostly in materials and matter, and of course in those research areas we have research fields where we are focusing, but of course there are also additional fields of research we do, because not everything can be pressed in just 5 research areas, and furthermore a university has to be flexible, has to be a living organism, and there must always be place for new ideas. Here you see the funds we get from grants, and you can see that there is a relatively even distribution now of the money we get from the National Science Foundation. In Austria it's called FWF. The funding organization that supports the cooperation with the industry in the national frame, the FFG, then of course EU money and direct industry cooperations, which also brings a lot of money to our funds. Here you see the study programs and the registered students. Not surprisingly, architecture is the most crowded curriculum, followed by informatics closely, computer science. Well, young people want to work with computers, we know that. And of course, we have a mixed bag. Chemistry, you see here in the center, about 1,400 students, but this is just the number we can easily handle with our resources. Here you see the teaching programs. Usually we have one bachelor curriculum per faculty. In some cases there are more one, but of course, in addition to those bachelor curricula, we have also master programs, and usually here you can specialize on different aspects based, of course, on your bachelor curriculum. What we also have is inter-faculty curricula. You see it on the bottom left, material science and biomedical engineering, which can be taken based on quite a number of different bachelor curricula. For example, mechanical engineering, electrical engineering, chemistry, physics, civil engineering, and so on. Here you see the further master programs. In technical chemistry, we have just one master curriculum, but you can specialize in different aspects, for example, material science. And of course, we also have doctoral programs. Those are very important for us in chemistry because for graduates of technical chemistry, the industry is usually expecting that they have a doctorate degree. And therefore, about 60 to 70% of our master graduates continue to obtain a PhD. We are not exclusively a technical university, but we are not exclusively working technically. You see the TU Ball. This is the oldest and most traditional ball dancing festival we have in Vienna, founded in 1815. We have also an orchestra, which is quite popular and also played in the Golden Hall of the Musikverein. You surely know from the newest concert. We also have musicians, the Bläser Philharmonie, and we also have a choir. That means our students are good in technology, but they are also good in cultural affairs. A few ideas about our graduates. Well, you know Christian Doppler, of course. The Doppler effect is very popular, except when you are caught by the police with radar. They also use the Doppler effect. Victor Kaplan. When I was here the last time, we visited also the power plant at the Iron Gate, and the turbines there are Kaplan turbines invented by Victor Kaplan. Richard Gigmondi, a graduate of chemistry. He won the Chemistry Nobel Prize in 1925. You could say he was one of the first nanotechnologists. Franz Fieberg, the first and so far only Austrian to be in space. And our most famous dropout is Johann Strauss. He studied for some time at our university, but then dropped out because with music he could earn more money. His brother Joseph even finished mechanical engineering, worked in his profession. He even designed a street cleaning machine, but then his brother convinced him music brings more money. Okay, we are located right in the city center, and in 5 minutes walking distance you have all those sites, from the Secession to the Opera to the Musikverein to St. Charles Church. They are all very close to our university, and if you have the chance to come to our university, you also have the chance to visit, for example, the Opera or the Musikverein. Okay, so much about the university. Now let's have a look on the Faculty of Technical Chemistry. Just a few data. About 200 staff funded from governmental sources. About further 200 funded from grants. That means we fund ourselves to a large extent from grants. In total, about 400 people. And here you have some budget data, of course. The main amount goes into manpower, well-paid manpower, as it should be, and also a lot of third-party funds where we fund mostly the staff, the 200, who are, let's say, mostly PhD, but also postdoc, master students, and so on. And they all are employed by the university and have the same benefits as the staff that is funded to governmental money. Now, a short look on my institute, Institute of Chemical Technologies and Analytics. 5 divisions: instrumental analytical chemistry, environmental and process analytics, structural and solid-state chemistry, mostly X-ray technologies, chemical technologies, powder metallurgy, my own topic, and technical electrochemistry. What are the subjects they are working? For example, short look on solid-state electrochemistry. Here we are using quite a number of different methods, both in electrochemical technology and also in chemical analysis. As I will show later on, this is one of our strengths, that we have close links between technology and characterization. And the topics that I worked at are those that are relatively hot at the moment in electrochemistry. Of course, the fuel cells, in our case it's solid oxide fuel cells, power to fuel, that means dissociating water by electrochemical technology to gain hydrogen, batteries, and a main focus, piezoelectric actors, because here the chemistry is very decisive for the long-time stability of, let's say, a diesel injection pump. This must survive 10 to 20 years in a very, very hostile environment. And this is linked to the chemistry, especially the oxygen content. As I already mentioned, we are also very strong in analytical techniques. Here, just an example, a time-of-flight secondary ion mass spectrometer used for the material we produce in-house, but also for jobs, for topics brought to us by the industry. For example, the electronics industry. Infineon is a very good partner. And on the right side, you see how we can make use of analytical techniques, in this case laser ablation, ICP-MS, to detect elements in specimens we have produced ourselves, to detect elements that otherwise are tricky to identify. But if you have the right equipment and if you have the expertise, the right people, then you can do also very tricky analytical jobs, which you have to do to know if the materials you have synthesized are okay or not. Well, chemical technologies, my division, you can simply say materials from powders. Metal powders, elemental or high alloy, carbides, nitrides, oxides, all materials that can be produced from powders are produced here, are investigated in our group. Why do we need materials from powders? What's the background? Well, it's very simple. On one hand, we can produce materials that are inaccessible by other techniques. It is, for example, the hard metal bits that are in this tunnel drilling machine that is shown on the bottom. Those are produced from powders and can only be produced from powders. And on the see on the top left, components of automotive transmissions. Surely you have powder metallurgy components in your car, because this production route, in this case, enables us to obtain high precision components in huge numbers and with very low material loss and very low energy loss. That means it's a green, a very economic technology. What are we doing? Well, if you have here the production chain for classical powder metallurgy, starting from the powder mix to compacting, sintering, and numerous secondary operations, what we are doing, we are focusing on the sintering process, and in particular on the chemical aspects of sintering. Sintering has been studied for many, many decades by scientists from US, from Russia, from Germany, from Wales, but most of the physical aspects, not so much the chemistry, but also the chemistry is very tricky. And to do this, of course, you also have to have the equipment to do similar processes in the industry, but in a very, very controlled way. And fortunately, as you can see here, we have all this equipment available. On the image, you see, for example, a so-called sinter hip furnace, where you can do sintering of hard metals, for example, at 1400 degrees, and you can do a pressure of 70 to 100 bars argon to compress the last remaining pores. What are our jobs to do? Well, on one hand, it's microstructural engineering. If you look on a conventional hard metal, you have the typical angular carbide phases shown in gray. But if you modify the shape of those carbides, you can improve, for example, the toughness of the structure without losing strength. And the same can be obtained, or a similar effect can be obtained, if we motivate the tungsten carbide crystals to grow into plates. This requires specific tricks with the chemistry and the sintering process, but if you know the tricks, you can produce hard metals that have very peculiar properties, which are, for example, important if you need high toughness, as, for example, in interrupted cutting, like in milling. Another feature that is very important from the chemical aspect is ultra-fine grade hard metals. We can call them nano. You see in the microstructure extremely fine for example, drills, micro drills. In your mobile phone, you have components that have very, very fine bores, and those bores are produced by hard metal drills. But you have to make sure that in the microstructure, all single tungsten carbide grains are submicron. A single larger grain will cause immediate fracture of the drill. That means controlling the chemistry of the system and therefore controlling the grain growth, preventing grain growth, is a very important item, and this is also subject of our studies. Chemistry is also important in that respect, since with hard metals, the window that is allowed to you to get sound material is very, very narrow. A few tenth % of carbon are decisive if you're successful or if you fail, because if you have too much, you end up with free graphite, which is a defect in the material, and if you have too little carbon, you end up with ether carbide, which are still more of a defect. That means controlling the chemistry through all the production process to end up right in the correct window of your hard metal. That is art that has to be performed. If we look on the ferrous components, the precision parts, just in an example, you see the powder, you see a specific microstructure on the top right, and you see some components for automotive transmissions, for automotive engines. Very popular at the moment are gears, and those, of course, have to fulfill the precision requirements and also the mechanical requirements over the lifetime of your car, and you want your car to live as long as possible. What do we do? Well, we consider what are the specific features of PM material. And here, compared, for example, to wrought steel, we have a very large specific surface, and if we take a compact and expose it to environment, we also have a very large interaction area. And this means that all atmospheric constituents can have a positive or negative effect on our component. What we also should consider is that this interaction area changes during the sintering process. It decreases, and therefore also the sensitivity decreases, and controlling also this process is also quite crucial. Another feature we have to consider, if we take a powder compact and we bring it into a sintering atmosphere, there is one atmosphere outside of our component that is the atmosphere we can control. But inside of the pore network, we have a different atmosphere that is controlled by the system itself. For example, if you have oxide on your powder particles, which you always have, and you want to remove this oxygen from the component, then the reduction process is usually controlled by the rate at which the reaction product, water, carbon monoxide, carbon dioxide, can be removed from your pore network. And to generate this, to motivate this, this is also one of the tricks you have to do when you want to have a successful sintering, especially when you want to do a sintering that removes you the harmful oxide layers you have on every powder particle. Just as an example how this can influence the behavior of your system, we are using thermoanalytical techniques to study the chemical reactions during the sintering process bottom left, you see the reduction kinetics of a standard carbon steel, a very simple system. And you see the mass change, the black graph, the mass change rate, the blue graph, and the mass spectrometer signal of mass 28, carbon monoxide. And if you look on this red signal, you will see that formation of carbon monoxide, which means removal of the oxygen, occurs below a certain threshold indicated by the black bar. This black bar simply indicates the temperature where sintering in standard conditions are done in a belt furnace. And you see that all the reduction process is more or less occurring below this temperature. And this means when you do the classical sintering process, you get oxygen removal virtually free of charge. You don't even recognize it. But if you go, for example, to a chromium prealloyed steel, which is a modern alloy system, you will recognize that part of the oxygen will be removed below that temperature, but if you want to get rid of all the oxygen, you have to go to significantly higher temperatures to remove really the oxygen and therefore to get all the mechanical properties you want to have in your component. And therefore our conclusion is, if you want to take advantage of the modern alloy systems, then you also have to adapt your sintering process to actually remove harmful compounds and of course also to form the sound metallic contacts that give you the desired mechanical properties. There are also phenomena that are relatively strange. One of those is, for example, the internal Getty effect. This is in fact a metallothermic reduction process. If you imagine you have a powder mix and you have components with different oxygen affinity, for example iron plus chromium or manganese or silicon, when you heat up the system, if you assume that we have, for example, carbon as a reducing agent, then iron oxide will be reduced at relatively low temperature in the early stage of the sintering process. This will generate carbon monoxide, carbon dioxide. But what we should not forget, for the alloy element, the silicon, the manganese, those conditions are still strongly oxidizing, and therefore what happens is indicated in bottom right. You generate carbon monoxide, you remove the iron oxide, but the oxygen that is set free is immediately gathered off by the alloy element particles which are oxidized. And this means that at the end you need significantly more intense reduction conditions to finally get rid of your oxygen. And you can see this to advantage when you study once more the reduction kinetics by thermoanalytical techniques. You see the graph on the left, iron carbon, we have already shown this. And on the right, this is simply iron carbon with some addition of manganese. And if you look, you will see that the main reduction peak is no more in the range 700 to 800 degrees, but it's rather in the range of 1200, because although iron oxide has already been reduced, manganese has gathered off the oxygen, and what you see here is simply the reduction peak of the manganese oxide. Therefore, the decisive criterion here is which temperature do we have to generate the thermodynamic conditions actually to reduce also the oxides of the most stable oxide forming element in your system. So much about ferrous. Let's have a look on another system where chemistry is quite decisive. This is aluminium powder injection molding. You know powder injection molding, you know polymer injection molding, you all are using components. If you mix the polymer with a metal powder or a ceramic powder, you do injection molding, and then you do a treatment where you remove the polymer and then you do a final sintering. You can get components with very intricate shapes from specific metals, but so far not from aluminium. Why? Well, the main explanation so far was it's simply the effect of the oxygen. Oxygen on the aluminum particles that prevents sintering. But nobody was able to actually cope with this. Our notion was it's not so much the oxygen, we were afraid of the carbon. from the binder, from the polymer, and therefore we developed a technique to remove the oxygen completely before the sintering process. And you see in bottom right, this actually has been successful. We were able to produce components that had very low carbon content, the red symbols, also very low nitrogen and also oxygen contents. And this actually enabled us to obtain proper sintering as indicated by the high density. That means only if you're able to control all interstitials, not only oxygen but also carbon and nitrogen, then you are able to produce sound components. And here you see the first demonstrator parts. On the one side, on the left, the green part, injection molding, on the right, the sintered one, and you see the shrinkage, you see the system actually has been densified. Here you see on the left how we did it. Well, it was a rather daring approach. We simply did the debinding in oxygen atmosphere. Well, you will think oxygen affinity of aluminum is very high. How can you do a treatment in oxygen without completely oxidizing a system? But if you do it in the right temperature window, the oxide layers are so stable, they are even stable against first oxidation. And therefore, what we ended up is a system where you simply burn off the binder without causing oxygen pickup of our system. And this is currently in the process of being introduced with one of our industrial partners. I already mentioned the lifetime of components. Lifetime of components mostly means fatigue, corrosion, and wear. We are dealing to a large extent with fatigue processes, and we are using a technology where we have ultrasonic resonance testing operating at 20 kilohertz. And this means that we can go to very high loading cycle numbers. Typically, we test to 10 billion cycles, 10 to the power of 10. And if you take a standard fatigue testing machine, this would take you about 8 years for one single value. We do it in 5 days. And this enables us to show, on one hand, the behavior of a metallic system without the limit of the high loading cycle numbers. We test to 10 to the power of 9, 10 to the power of 10. And what showed so far is, rather surprisingly, we never found a true fatigue limit. If you look at the textbook for mechanical engineering, civil engineering, you will recognize that the SN curves always have a horizontal branch to the right. But so far we couldn't find this. Because we can test right to very high loading cycle numbers. And if you look on some cases of damage in applications where you have really high loading cycle numbers, it ends up that also the industry, for example, people who are operating railways, they are recognizing that they have to consider testing not only to 1 million cycle, but at least 1 billion, because the behavior of the material is different. In particular, when you have singular defects. Here, for example, on the bottom left, you see a carbide inclusion in a tool steel that caused fatigue fracture at very high loading cycle number. And bottom right, you see a diagram, a so-called Kitagawa-Takahashi diagram, where we can assess how damaging a defect is in our system. And if you look on the diagram, you will recognize the better, the intrinsically better your material is, the more sensitive it is to defects. Because the intersection between the horizontal and the angled line gives you the size of a defect that starts to be harmful. And you see, we have here one limit, relatively low strength, we have here high strength, and the intersection is moved to the left. That means the moderate strength material can tolerate larger defects than the high strength, and therefore if you want to go into highly loaded applications, you have to produce extremely clean systems, especially if we go to systems where we have high loading cycle numbers in fatigue. This fatigue testing is, however, not only applicable to structural parts, but we also apply it to electronics. If you look, for example, in the locomotive, you have power electronics there, And you have to grant that the lifetime is 30 years or more. And those IGBT modules, for example, if you overload them, you end up with what is shown here on the top, on the bottom right. There will be electronic failures. And here we have very high currents, 400 amperes, for example, for such an IGBT. Therefore, this can do a lot of damage if, for example, the contacting of such a system fails. How can we test this? Well, of course, the industry is doing power cycling. That means they are running the system under load, then switching off, applying the load once more, therefore causing a thermal cycling. But this thermal cycling is slow. 1 Hertz is extremely ambitious. Usually cycling is slower. That means simulating operation of a locomotive for 30 years is very, very time consuming. Our approach is that the damage that is caused by the thermal cycling is in fact the damage that is done by mechanical cycling. And there we apply our technique, our ultrasonic technique, to run the system to very high loading cycle numbers within a reasonable time. You see here the graph on the bottom, where we have the power cycling, slow, with low loading cycle numbers, while our ultrasonic testing enables us to test to high loading cycle numbers within a short time. You see on the left, ultrasonic, testing time 15 hours. On the right, standard power cycling. The same test, the same cycle number takes 10 years. And that's something, of course, nobody can afford to do. That means this testing technique enables us to simulate the loading conditions, the practical loading conditions of a system within a reasonably short time. And this, of course, enables us to give our partners very, very short development cycles. Okay, so much about our activities we are doing in my group. I hope to see many of you in Vienna with a view to St. Stephen's Cathedral. This is a view from the top of our tower building, where we regularly have meetings, one of the nicest places. If you have the chance, come to Vienna and I take you up there. Once more, many thanks for the honor, and I'm looking forward to a further cooperation. Thank you.
Dear Professor Danninger, thank you very much for this exciting presentation. You give us some insights in your university, in your department. It was very nice to hear, especially for our young students. Probably the cooperation between our institution could bring few of them to Vienna. It will be very, very nice for them, I'm pretty sure. Let me confess that I'm also pretty sure our university this time grow and became stronger with you here in the corpus Doctor Honoris Causa of our institution. Stimați invitați, stimați participanți, trebuie să-i mulțumim domnului profesor. Sunt convins că a fost pentru voi toți o ocazie plăcută să aflați câte ceva despre Universitatea Tehnică de la Viena, într-adevăr situată în centrul orașului, într-o zonă minunată, și să luăm de bună invitația domnului profesor de a vizita, de a colabora cu dumnealor. Da. Once again, dear Dr. Honoris Causa of our university, congratulations and all the best. Now I have to close the ceremony and to invite you to have a cup of champagne here near this blue hall. Deci, mulțumim pentru participare și vă invităm la o cupă de șampanie.